Alright everyone, welcome back to the day 15 of our daily leetcode challenge, and today we have got minimize XOR. Now this question is a bit manipulation problem, and we'll see how we can do this using bit manipulation and what they are asking us to do. Let's understand that first. So in this question right here, they have provided us with two numbers, num1 and num2. Now these two numbers right here that they have provided us, they want us to get another number said x. This number x has to follow two properties. First is that the number of set bits, now what they mean by set bits is that the number of ones in the binary representation of both these numbers x and 2 should be same. So let's say that the binary representation of 2 is something like this, then the x should definitely have 3 set bits. It could be in any order, but it should 100% have 3 set bits, or it could be like this as well. So that's what they mean when they say that the number of set bits should be same. That's condition 1. The condition 2 is that the XOR between x and the number 1 should be minimal. Now what is an XOR operation? XOR operations, as in, let's say you have binary numbers like 0 0, 1 0, 0 1 and 1 1. The XOR operation between each of these bits, whenever they are same, it's a 0, and when they are not same, it's a 1. So this is how the XOR operation works. Let's say I want an XOR operation between 1001 and 1001. So the XOR operation with any number with its own XOR operation is always 0. So we will kind of use this property right here that we just saw, XOR operation of a number with itself being 0 or being minimal is what we're going to use. So if you just notice something, they have clearly mentioned here that the XOR operation has to be minimal with a num1, and with num2 they should have the same number of bits. So we are kind of getting somewhere here. What they want us to do is, like, if you see right, we just now saw that an XOR operation with its own number, like let's say 2 XOR 2 or any number XORed with itself, is 0. So we can say that alright, at least we can start with that like in this condition, or in whatever condition they might provide us, we can at least start with number 1. We can initially assign x to num1 and then say that alright, this is my starting point, this is my starting point as x. Now we'll have to just simply modify x, and in modifying I mean like we have to see where and all we can get the set bits in x modified so that it matches with 2. That's what we have to do. We'll start with num1, x being num1, so that the XOR operation is minimal. Now we need to modify x. Modify as in we need to update its set bits. In places of zeros, we'll have to basically make changes. We could have x having 3 ones or 4 ones or any number of ones. We eventually have to make it equal to the number of ones in 2. Now how are we going to do that? So if you take a look, right, there are 3 possible conditions. Firstly, the number of bits are same. That would be condition 1, that the number of bits in x and number of set bits in num2 and x are same the moment we see num1, the moment we set x as num1. In the very first step, the moment we set x as num1, we see that the number of set bits are already same. In that case, we just simply return x as it is. We saw that x, when we set it as num1, we saw that in the binary representation of x and in the binary representation of 2, the number of set bits are same. Immediately we just return x as num1. If you take a look at the first example, you see they immediately return 3 as the answer. The reason behind that is because what I just said was the reason behind it. Because if you take a look at the binary representation of 3 and 5, this is num1, this is num2. In the binary representation of 3, it looks something like this. The binary representation of 5 looks something like this. Initially, as I discussed, we'll set x to num1, and the moment we set x to num1, we saw that the number of 1 bits in x, which is right now 3, is same as that of 5 that they provided, so we immediately return 3. So that is the case when the number of set bits is equal to that of num2 initially. So if that happens, we simply return x, so we don't have to worry about that, that's gone. The second and third cases wherein the number of set bits in x is less than that of 5, and the third case is that number of set bits is more in x compared to that of 5. So if we take a look at the second and third example, let's work with that. So we already discussed what will happen if the number of set bits is same for x and num2. We just simply return x, as we saw in example 1. That was the reason why we immediately returned 3. Now let's take a look at the case where the number of set bits is actually less than that of num2. So for that, let's take the example of 9 and 7. Here 9 is num1, 7 is num2. If you take a binary representation of 9, you will see it looks like this, and the binary representation of 7 looks like this. Now if you see, initially, as we said, we have to set x as 9. So initially x is 9. Now we somehow need to modify this 9's binary representation, which will initially be like this, so that the number of set bits, which is in 2 in this case, goes up to 3. Now we have to decide where and all we will have to change the zeros to 1, because in this case, since the number of 1 bits in x is less than that of in num2, we see that x has initially 2 set bits, 7 has 3. So clearly we have to increase the set bits in x so that it matches that of num2. Now where and all we have to make those changes. So now let's kind of draw both these numbers right here. Initially x is 1 0 0 1 and 7 is 0 1 1 1. Now if you know, in binaries there are two values. One is there are two places, like on the extreme right, on the extreme left, on the extreme right. The more right you go is like the most least significant bit, and the more right you go is the most significant bit. What I mean by that is, you know how binaries work. For example, here this is nothing but powers of 2's. This will go 2 raised to power 1, 2 raised to power 0, like that. So this is the most significant bit right here. So because of that, this changing this value right here will have a major impact compared to this value. This is why it's called as the most significant bit at this point, and this is called as the least significant bit. Now we are tasked to change bits in the number x, and we also have to make sure that the XOR operation between this number and this number, which is same right now, should be minimal. Now since we want the XOR operation to be minimal and as well increase the bits, we should always make sure that we do that from the least significant to the most significant, which is, by that I mean, in this manner. In this manner we should increase the bits from the very far right to far left. In this manner we should increase the bits. So if you take a look at the last index, we see that alright, the bits are already same, so we need not do anything. Then we come here, we see that here is a 0 and here is a 1. We see that the count of 1 bit so far is 2 in this case and 3 in this case. We need to increase this count to match this. We could have changed it here as well, we could have changed it anywhere else as well, we can change it anywhere else, but the problem is we want to make sure that the XOR between these two values is the least, and to make sure that, we should always make those changes from zeros to 1 from the left to right. So we already see a 1 is already here, we can't do anything. We see an empty slot here, so let's set this to 1. The moment you set this to 1, you see that the count becomes equal now. We stop doing any further changes, and we are gonna simply return this value right here. This would be the new value of x. Now this value right here satisfies both conditions. Firstly, the XOR between 9 and this number is going to be minimal, and the number of set bits between this one and this 2 is going to be same, which is 3. Now if you quickly do the XOR between these two values, right, you will see something. The XOR between 9 and this number, so we get a 0 here, 1 here, 0 0. Now this is nothing but 2, and the value that we just got here, 1011, is nothing but 11. So the answer in the case of 9 and 7 will be 11. Our x would be 11. Now this is the case where the number of 1 bits in x was less than that of num2, as in we had to increase the number of 1 bits in x in order to match the condition where 7 had 3 bits, so it had to match that condition. So we kind of increase the count of 1 bits in x. Now let's take an example where the number of 1 bits in our x initially defined is more than that of num2. In that case, we'll have to reduce the 1 bits. Now let's see how we want to deal with that. So this was the case where the number of 1 bits are actually kind of greater in x initially. Sorry, they are less in x initially, so we had to increase the 1 bits, as we just saw. So this is the case of that. Now let's take a case where the number of 1 bits are actually less in like actually more in num1, which is x. Initially the number of 1 bits are in x that we defined are greater than that of num2 initially. So in that case we'll have to reduce the number of 1 bits in x so that it matches that with num2. So in the case of 15 and 7, in the case of 15 and 7, if you see, the binary representation of 15 looks like this, the binary representation of 7 looks like this. Initially, as we said, we will set x to 15, which would be our x will be looking something like this. Now the XOR between these two is going to be 0, so this is minimum, this is the minimum we can get. Now we need to modify this so that the second condition is also met, the number of 1 bits should match. Now let's put them side by side. Now we'll have a look here. We want us to convert this number such that the number of 1 bits here reduces from 4 to 3. Now how we can do it? We can set this to a 0, or we can set this to a 0, or we can set this to a 0, or we could set this to a 0. Now it's up to us to decide which index to put the 0 to. Now again, since as we discussed earlier, we want to make sure the XOR between them is minimal. Any changes you make on the least significant bit side will have a much lesser impact compared to the changes made on the most significant bit side, because that's how binaries work. We have to prioritize making changes from least significant side to the most significant side. Now what our task is to at least to reduce the count of 1 bits from here, from whatever count it is, to this. So we find that it's 4 here and we need to bring it down to 3. Now we are at the first index, we see that it's already a 1 here and already a 1 here. We need to make sure that at least, alright, if we unset this one, to 0, our condition is gonna match, and in that case we will have the count back to equal as well. We could have done this here as well, or here as well, but these value changes is gonna have a major impact in the XOR. So in order to reduce the XOR, let's just make a change here. Now the count gets reduced from 4 to 3 and our second condition is also met. So the final answer in this case will be 1110. And if you do the XOR between this value and 15 right here, you will see it's just 1 and all these will turn to 0. So this is also again set to minimum, the minimum we can actually get. So I hope you are getting the point. This is what we are gonna do. Now in order to code this up, we can use all those fancy XOR operations and stuff like this or like this, but I won't be using that. We are actually gonna use strings and lists in order to form binary strings and modify them exactly how we just saw here, and then in turn return the answer. So let's quickly code this up. We're going to follow exactly what we said. Firstly, what we need to do is convert these num1 and num2 to their binary representations. In Python you can quickly do this using this index. So here num1, to convert this to binary, I can simply say this stuff right here that you see is called as f string. This is converting this num1 to a binary format and assigning it to a variable num1. Num2 is going to be the same thing to its binary form. Now we need to make sure that the length of num1 and num2 is same, because you know, in sometimes if you take a look, right, if you take this example right here, if I use the method that I just showed you, it will not include the 0 here, it will just return me 1 1 1. We want to make sure that the length of the binaries are same. By what that I mean is, if let's say it's only 1 1, it should add zeros on the left on this side of the string on its own, even though it won't make any changes to the value, but we need to make sure that the length is same, because this comparison operation that we are going to do we have to make sure the length is same. So in order to do that, let me just find what is the max length. Any one of them is going to be either greater or equal to. So let me just find that. We are comparing the length, max based on the length. So whatever the length is, we have to make sure that the num1 and num2 are both equal to this length. So how can we make sure of that? just quickly just do a quick difference. In the length, and accordingly we'll have to add zeros of that length on the left hand side. So something like this for num2 as well. This is a quick operation that we are doing in order to make sure that the length is same. This is why we are adding those extra zeros as we discussed. Now if I just print these num1 and num2, we'll see something. This is nothing but the binary representation. So in the case of 3 and 5, we'll get the binaries 1, 12, we'll get the binaries 9, 7 and 15, 7. They're binary representations. Alright, this has to be a length as well, I'm sorry. Yeah, you can see these numbers converted to their binary formats, all of them, as we discussed. 15 and 7 we just saw, it looks something like this, 1 1 1 and 0 1 1. Same for 9 and 7. Now as we said, our initial x will actually initially be equal to num2. So let me just define our res as num1 initially. Now again, as we discussed, if the count of 1, count of 1, which is the set bits in num1 and num2, there are actually always 3 cases. Either they are same, or in num1 it's less, or in num1 it's more. It will either be same, less than, or greater than. So let's just store the count of the ones for num1 and num2 in separate variables. So count 1 is gonna be num1 dot count, and count 2 will be num2 dot count. If count 1 is equal to count 2, this is our first condition, we just simply return res, which is num1, right? But then again, this is in binary format, so we need to convert it back to integer. So this can be quickly done using this. We'll have num1 right here, or we can have res here, and then convert it back to integer in this format. So this is gonna return it. So if you take a look, right, in all these cases, I think this test case is gonna get satisfied for this condition. So for this test is what the remainings will fail. So let's now code the other parts as well. The second condition is if count 1, which is the number of set bits in num1, is less than that of num2, as we saw, right, in the previous one, in the case of 9 and 7, where this number of set bits in num1 was actually less than that of num2. So we discussed how we're gonna iterate from the very right hand side and do all those modifications. Now these num1 and num2 are actually strings, so strings cannot be modified, but list can. So what we need to do is convert these num1 and num2 back to a list. So in order to do that, I can either define new list here, or we can just simply convert this string right here that we just formed to a list directly by writing list method, by wrapping this entire thing in the list method. This will directly convert it to a list. So we can do that instead, and we'll make no change. Instead of string, this will now become to a list. I can print it here to show it to you guys. Alright, let's run this. So instead of showing us a string, right, it was showing like this, it's gonna return me a list. We'll deal with this later, let me show you. So it's showing me as in the form of list now. Now we can do the operation that we were dealing with, comparing all these binaries from this side and making changes as we discussed. So to do that, again, we have two counts, count 1 and count 2. So if count 1 is equal to count 2, we can simply return this num1. See, the reason we were getting an error was because now num1 is a list, and we cannot simply convert that to binary directly. From a from a list you cannot convert it to a decimal. You have to first convert it back to a string first, and then to a binary sorry, decimal. So we'll have to do this join operation on a list. Res initially right now is a list, since we converted back to a list. Now this is a string. Now we need to convert it to an integer decimal. So that is why we are doing a 2 right here. So that's the case when count 1 is equal to count 2. Now let's deal with the case where count 1 is less than count 2. Now again we need to set the bits of count 1. We have to increase the bits of count 1 in order to match count 2, right? And we have to do that from the least significant bit, which is from the very right. So this is how the code will look like. Here -1 -1 -1 means we are starting from the very last index, which is from the least significant side, up till all the way till -1, which is like up till the last, which is 0th index it will go up till, and you have to keep on decreasing the indexes, so that we keep iterating from the very right, from the least significant to the most significant, right? Now what did we discussed in the case of 50, in the case of 9 and 7? If num1 are is a 0, and num2 is a 1, this is the case where we need to shift this 0 to a 1 from the least significant side, right? And we'll have to increase the count as well. So two steps are going to happen. First is num1 will be assigned to a 1, and the count of 1 will be increased, and the moment this count becomes equal, we'll have to stop doing this. You have to simply break. We'll have to break this loop. We are starting from the least significant side, from the left side, and going this side, and if the moment we see that we have a 0 here and a 1 here, we should change that to a 1. That's what I am doing here. The moment we see it's a 0 here and num2 has a 1 on the corresponding side, you have to change that to a 1 from the least significant side, increase the count of 1, and when the moment the counts are equal, we should break the loop. Now the same thing will happen in the else case, where the count 1 is actually greater. Now same thing, we'll have to do the for loop again. Instead of num1 you could also use num2, it doesn't matter because the length is same. Now if num1, we see that num1 is a, now in this case what we need to do is we need to reduce the 1 bit. So we see that if it's a 1 here and num2 r is a 0, because in this case that we saw, this is the case, right? We started with a 1 1 1 1 and 0 1 1 1. We need to reduce the bits from 4 to 3. So where can we do that? We should start from the least significant side. So if we see that it's a 1 right here and a 1 right here as well, then we can change this to a 0, right? We can reduce this. So basically that's what we are doing. If it's 1 there, then also it's not an issue. Alright, so I just realized that we don't need to do at line number 19, if you see that the other condition that we are checking of num2 r is equal to 1, this is not required, because as we saw in the map as well and saw in the diagram as well, we are doing this operation from the least significant bit to the most significant. So in order to in count 1, we are basically trying to increase the count of 1 in num1. So whenever we find a 0, it is definitely going to be at the least significant bit, so we set that to 1. And the same thing is coming when we are trying to decrease. Every time we encounter a 1, we have to do the same thing and reduce it to a 0, and we have to don't check anything else. We just simply need to check at the least significant. The moment we find a 1, we reduce it to 0, and the more we do it at the least significant bit, the less impact is going to have on the XOR values. So this is why I remove those extra conditions. It's not required, and once we do that, we will find that the num1 modified converted back to a string and converted later back to a in decimal value. So if we now try to submit this, all our test cases will be satisfied. Yeah, 3 5. In the case of 15 and 7 as well, the answer was 14. So let's try to submit this. Yeah, so as you can see, it beats almost all the solution, and this is how you try to like do this without using those fancy XOR operations. We simply kind of did exactly what we were discussing here, converted to a string, converted to a binary, and then compared values at the least significant bit and modified them accordingly. So that was it for today. I'll see you everyone. I'll see you guys tomorrow. Bye.